So today on Exciting Chemistry Videos for the Pandemic, we're talking about measuring concentration. So remember, concentration is just how much solute is in the solution. So you can have something that's saturated, meaning it's completely filled, unsaturated, meaning it's not completely filled. Uh, you can even have supersaturation, which we're not going to talk about so much in this episode. In general, though, we tend to refer to solutions as either concentrated, which means it has a lot of solute in it, or dilute, which means it has relatively little. Now, these concentrated and dilute are terms kind of like hot and cold or warm and cold. They're just relative. There's not a certain amount that means concentrated and a certain amount that means dilute. It's just relatively more or less solute in the solvent. So again, this is the difference between like the big boy acid that they ship that I get that's 12 molar that, you know, if you spilled on your hands would be a big problem, and the much less, either 1 or 0.1 molar hydrochloric acid that I give you guys. I dilute it out. Uh, it's also, you know, the difference between having like Kool-Aid with lots of sugar or Kool-Aid with a little bit of sugar. One is more dilute, one is more concentrated. Uh, and for chemical reactions, it's really important to know how much solute is in the solution, because it's usually the solute that does the reacting. A lot of reactions take place in water. And remember, for our purposes, we're going to be talking about water as a solvent for pretty much all of our solutions. So water is going to be your solvent. That's not 100% the case all the time in like life, but for our purposes, it will be. And most of the time in chemistry, water is going to be your solvent. When what goes on in those reactions, when those things react, is it's the solutes that are reacting. So it's really important to know how much solute is in there to know how much reaction you're going to get. So there are 3 common ways to measure solutions: molarity, percent by mass, and percent by volume. From a chemical standpoint, molarity is by far the most important. It is the one that helps us out a lot, because when we're dealing with chemical reactions, we're dealing with moles of reactants and products. Percent by mass and percent by volume, you would actually have to end up converting those into molarity before you even do anything with them, and it's just a pain. But they can help people who don't really understand the depths of chemistry just kind of get a good idea of how much stuff is in there. So a lot of products are given in percent by, like consumer products are given percent by volume or percent by mass. But from a chemical standpoint, it's not as helpful. So whenever we're talking about concentration, we're talking about how much solute is in the solution. And we're going to focus primarily on molarity, but I will go over the equations for each of them. So molarity is moles of solute divided by liters of solution. So moles per liter. Percent volume is volume of solute divided by the total volume of the solution. Percent volume is what you see with lots of things, but for instance, alcohol. If you buy beer or wine, it will have an ABV, alcohol by volume. That's the percent of ethanol in the volume, in that volume of beer. So if you have a 12-ounce bottle of beer and it's 5% uh, ethanol, 5% alcohol by volume, you know you have 5% of 12 ounces, or zero 0.6 ounces, and yes, American units are terrible, but 0.6 ounces of alcohol in that whole amount of beer, in that whole solution. Also, proof for harder liquors is a percent by volume too, but it's a weird system. It's percent by volume doubled. So 200 proof would be pure alcohol, and 40 proof would be 20% alcohol. I don't know why they did that. The name proof is kind of interesting. You used to have to prove what percent you were selling it at. Like you go get a stamp that said this alcohol is as much alcohol as we're saying it is, so you couldn't lie about it. And one of the tests they used to do for proof was to see how long, so they'd soak the alcohol or soak gunpowder in the alcohol and see how quickly it burned. So there's not a whole lot that's more American than testing your alcohol with gunpowder. So America. Percent by mass, just mass of the solute over mass of the solution. That's used sometimes too. Again, it's a quick way to understand how much is in there, but from a chemical standpoint, you're going to turn mass into moles anyway when you end up doing any actual chemistry with it. So for our purposes, molarity is the most helpful one for anything we'll be doing. So let's do a molarity problem. IV saline solution. Uh, generally contains 0.9 grams of sodium chloride and exactly 100 milliliters of solution. What is the molarity of solution? So this is not a hard problem. Molarity equals moles divided by liters. So we need to find out moles and find out liters. So moles NaCl, well, we have 0.9 grams NaCl over 1. Sodium chloride is 58.44 grams in 1 mole. And I'll come back with that answer once I do some calculator button pressing. Okay, so finishing up that problem, you see that we have 0.015 moles of sodium chloride. That's just 0.9 divided by the molar mass of sodium chloride. I have also figured out how many liters of solution we have total. I'm sure most of you can do this in your head, but I have shown the actual work here. You don't have to show work for milliliters to liters. I assume you guys can move decimals, but you end up with 0.1 liters of solution. So if we want to go moles per liter, all you have to do is, so molarity, molarity equals 0.015 moles over 0.1 liters. And this one I can do in my head. So you end up with 0.15 molar NaCl. Molarity, by the way, is abbreviated with a capital M, and it has to be capital. There's enough things that are M already, but molarity is a capital M. So whenever you do molarity, it's a capital M, and usually we write it as 0.15 molar M, like capital M after sodium chloride. So that's usually how we write that, and that you've probably seen on solutions that I've done. Also, by the way, I did put the abbreviations for percent by volume and percent by mass here. They're pretty easy to understand, though. So intravenous saline is about 0.15 molar sodium chloride solution. Not super hard, but you do need to know how to do it. So here's another thing that you might eventually have to do, especially if any of you go on to science, like you have to make up solutions. I do this all the time in the lab. I still do it all the time when I'm prepping labs for your classes. I have to make up solutions that have certain concentrations. So how would you make 700 milliliters of a 0.5 molar calcium chloride solution? So first of all, molarity equals moles divided by liters. And what I really need to know is how many moles of calcium chloride I need, and then I'll convert that to grams. Because whenever we make a solution, if it's from something solid, we weigh it out in grams. So moles, and I'm just rearranging this, equals molarity times liters. And in this case, moles equals 0.700 times 0.50. Again, I switch milliliters to liters in my head, and that will equal 0.35 moles. So I need 0.35 moles of calcium chloride, and we can figure out how many grams that is. It's just a moles to grams conversion, so 0.35 moles of calcium chloride over 1. Calcium chloride's molar mass is 110.98 grams per 1 mole. Yeah, the stoichiometry stuff, it really never leaves. We do conversions just all the time. These are a little less complex, but again, here we are still doing them. So 0.35 times 110.98 is 38.8, which I'll choose 39 grams of, nope, not NaCl, CaCl2. So we need 39 grams of CaCl2, and we need to put it in 700 milliliters of total solution. One thing, and I'm not going to test you on this, I used to test kids on this and we'd have to do it in the lab. When you make a solution, there are actually 3 steps because you can't just put 700 milliliters of water in a beaker and then add. So if I have a beaker and it has exactly 700 milliliters of water, if I add any CaCl2, what I will end up with is obviously something that has slightly more than 700 milliliters. So we'll put 700. I don't know exactly how much more, but you want to end up with exactly 700 milliliters of water. So in order to do that, it would be 3 steps. What you do is start with half the volume of water, in this case 350 milliliters, or 0.35 liters if you prefer. Add the solute, in this case 39 grams CaCl2, and then you might want to stir to dissolve. You want it all dissolved, but that's not super important. And then fill up to desired amount. In this case, 700 milliliters with water, or whatever your solvent is, but for our purposes, water is always going to be a solvent. So you can't just start with 700 milliliters of water, because then if you add anything, you'll end up with more than 700 milliliters of water, because, you know, stuff takes up space. So that's molarity, and that's how you make a solution. The other thing I want to talk about today is dilutions, diluting concentrated things into less concentrated things. And there's an equation for that, and it's pretty simple to understand. Remember, molarity equals moles divided by liters. So if molarity equals moles divided by liters, that's moles of solute divided by liters of solution. Moles equals molarity times liters, or molarity times, in this case, volume. Well, when you dilute something, if I have, let's say, 10 molar calcium chloride, which would be very impressive. Well, let's just say 10 molar of whatever, 10 molar of a solution. If I dilute it by adding water, and let's say I add water so it's at twice as much volume, and yes, my drawings aren't to scale, but life will go on, I will end up with, here, maybe 5 molar of X solution after the water has been added. What changes is the amount of solvent you added, the amount of water. The moles of solute doesn't change. So in a dilution, the moles of solute doesn't change. So that's all this equation up here says. The moles of solute, molarity times volume, stays the same. The moles of solute before dilution is the same as the moles of solute after dilution. And that is why, because when you add water, you are changing the molarity, but you're not changing the amount of solute that's in there. So that's what a dilution is. There's lots of reasons you do dilutions. Most commonly, because you tend to have what are called stock solutions, which are kept at high concentration because they're easier to ship, and then if you make them once, you can dilute them out many times into smaller, like usable solutions. So like again, when we get hydrochloric acid, it's 12 molar. We get a couple liters of 12 molar hydrochloric acid, and we dilute that out to 1 molar or 2 molar, maybe like 0.5 molar, whatever you guys happen to use. But it ships, and we store it in the stock concentration, because otherwise you're just storing a whole bunch of extra water or shipping a whole bunch of extra water, which costs more money. So you keep it in generally the stock solution, and when you need some, you dilute that out to whatever you need. So let's say we have a 2 molar magnesium sulfate solution, and we need to dilute it to prepare 100 milliliters of aqueous 0.4 molar magnesium sulfide, or magnesium sulfate, excuse me. So all we need to know is this is molarity 1. We're looking for the first volume, how much we need to dilute. This is volume 2, and this is molarity 2. By the way, volume in this case can be either in milliliters or liters. As long as both sides are the same thing, it doesn't matter because they'll cancel out. So M1V1 equals M2V2. We are looking for volume 1 here. Volume 1 is going to equal molarity 2 times volume 2 divided by, molarity 1, not volume 1 there. And so I'll set this up and come back. So I did the math really quick, and you find out that the amount you need to start with is 20 milliliters of the stock solution. So you'd start with 20 milliliters of the stock solution, the concentrated solution, and you dilute it with water until there is 100 milliliters. Now, generally, that's going to be pretty much 80 milliliters of water, but solutions don't always conserve volume. Usually they do as long as they're aqueous. But not always, so I don't like saying exactly. I like to say dilute 20 mils of stock solution until you reach the desired volume, which is how you would do it anyway. You'd take it, put the 20 mils in a graduated cylinder, and then fill it the rest of the way. So that is molarity, also percent by mass and percent by volume. Those are important things you'll see because you'll actually see them at the grocery store and stuff, but for chemistry, not as important. There is also a whole different set of measuring concentration I'm going to very briefly touch on. I'm going to go through an extra PowerPoint I made, and if you're interested, you can look at it in more detail, but I want to talk about it very so there's this PowerPoint that I have that's addendum concentration, and you can look at it if you're more interested. There's some stuff in here that gets used, and these are all different ways of measuring concentration that are used in chemistry. Molarity is by far the most common. But there's also parts ratio, which is, if you've ever heard of parts per million or parts per billion, that's what it is. Mole fraction and molality. Molality, which is cleverly named to be very confusing with molarity, is moles of solute per kilograms of solvent. And there are occasions when that one makes more sense to use than molarity. That'll actually be the next section we talk about. We won't be measuring molality, but it's a thing we use in chemistry. So I just want to talk briefly about parts per million and parts per billion. So percent concentration going on. But parts per million and parts per billion are somewhat interesting because this is how they measure things like how much chlorine is in a pool or rates of air pollution, stuff that's really, really tiny. So when really, really tiny solutions. So when we talk about air pollution, we're usually talking about how many parts per million or parts per billion the pollutant is in air, because air pollution is not like the majority of air. It's small amounts. It doesn't mean it's healthy or good, but it's relatively small amounts. Or if you think about how much chlorine you put in a pool, not a lot of chlorine. In a pool, it's like 10% chlorine. That would be bad and, deadly. So you want a very small amount, just enough to kill off bacteria and keep the water clear. There's some examples here, but parts per million, parts per billion are something you might hear, and they are used, and this is how we get them. Mole fraction is weird, and you do use it occasionally in chemistry, and molality is also used, and that'll be used for what are called colligative properties, which is what we'll do in the next section. And colligative properties are important, but I'm not going to make you learn how to do molality. But if you're more interested in this, there is an addendum PowerPoint that I will put up on PowerSchool. And just be aware that there are other ways to measure solution. Molarity is what we will most commonly be doing. Molarity is the most important because it tells us the most about our solutions as far as how we use them. So it'll tell us about how many moles of solute you have in there, and that's usually what you need for a reaction. Okay, that's it for today. Have a good day.